Telescopes, lesson 2, reflecting telescopes and resolving power. So there's no calculations in this one, it's basically just notes, useful information. So reflecting telescopes use a concave mirror or of long focal length as an objective to collect light from distant objects. So the eyepiece is a short focal length converging lens, is same as in the refracting telescope. And the equations used for refracting telescopes for magnifying power also apply for reflecting telescopes. So quite a big thing. So Mount Palomar Telescope in California has an objective mirror of 5 meters and was for many years the world's largest telescope. Right, and so Cassegrain reflecting telescope. So you need to learn this one. So obviously sketch it out, cover it up, practice sketching it out until you've learnt it. So you've got a small convex mirror and a concave mirror with a small central hole which leads to the eyepiece lens. So light comes in from distant objects, reflects due to the concave nature of the mirror, hits the small convex mirror, the beams cross over and hit the eyepiece lens. Quite a bit easier to draw than the refracting telescope, I believe. So the effective focal length of the objective is increased by making the secondary mirror convex. This allows the Cassegrain telescope to be shorter than a similarly powerful Newtonian. The Newtonian reflecting telescope, you don't need to, for the AQA specification anyway, you don't need to know that diagram anymore. Focusing is achieved by adjusting the position of the convex mirror. So you can move that either to the left or to the right. Alright, so there's another issue. So we looked at chromatic aberration in the last lesson. This one's spherical aberration. So the primary mirror, that's the big mirror on the right hand side there, that concave mirror. Primary mirror should be parabolic in shape and not spherical. Otherwise, the outermost rays do not focus at the same place as the innermost ones, as you can see on the left hand side. So you've got the light that's incident, reflecting at different angles, and you've essentially got yourself 2 focus points instead of 1. And this defect, when it occurs, is called spherical aberration. So in a parabolic mirror, you don't get that effect. Spherical is kind of just a more intense bending, greater angles. Parabolic mirror, you won't get that. All incident light will reflect onto the same focus point. Right, so this one comes up a lot in exams, comparison of refracting and reflecting telescopes. So refracting telescopes do not have secondary mirror, and it supports, because obviously you've seen the size of those telescopes potentially. So that mirror will need supporting, and both of those block out some of the light from the object. Refracting telescopes have a wider field of view than reflectors of the same length because their angular magnification is less. So, using a refracting telescope, astronomical objects are consequently easier to locate. And refracting telescopes, because the lenses do not suffer from spherical aberration. Onto reflecting telescopes. Can have much wider objectives because their mirror can be supported from below. This allows the telescope to detect much fainter objects and also allows greater magnifying powers without loss of resolution. Reflecting telescopes can be shorter, therefore easier to handle, than refractors of equal magnification. So if you've got a refracting and a reflecting that the same amount of magnification, the reflecting telescope will always be shorter. Reflecting telescopes suffer much less from chromatic aberration. And incidentally, the largest telescopes in the world are indeed reflectors. Alright, so let's look at resolving power. So this is the ability of a telescope to show detail. So it's like 4K versus 1080p. So 2 stars that are close to each other may appear as shown below. Stars are resolved. You can clearly see that the 2 separate stars. They could look like this, where they're only just resolved, or they could literally layer on top of each other at a lower resolution or not high enough resolution, and they'll appear to be a single star. So the higher the resolving power of a telescope, the better able it can show separately two adjacent stars. So diffraction at circular aperture. So the limit of a telescope's resolving power is due to the diffraction of light that occurs at the objective lens or mirror. So the objective acts as a circular aperture to light, and light from a distant star produces a circular diffraction pattern as shown in the diagram below. So the centre of that image is called an Aries disk, and then you've got, n equals 2, n equals 3, n equals 4, where you get constructive interference, you end up with a banding. So diffraction pattern consists of a central bright maximum surrounded by a circular minimum, which is further surrounded by further circular maximum, minimum, and so on. So light from two stars will form a pair of circular diffraction patterns like this. So in this instance, the images are easily resolved. So if the stars are close enough, the diffraction patterns will overlap, like this one. In this instance, the images are just resolved. The two central Aries disks, the really bright regions that contain most of the light, if they touch each other, so if this image at the bottom, if the central circular aperture patterns were a tiny bit closer together and the large red sections were touching, then the images are not resolved, and the resolution is not high enough to distinguish between two separate images. Right, next lesson we'll move on to the Rayleigh criterion, which will be the mathematical side of this. Alright, thanks for watching.